Albert Einstein gave us this absolutely wild and beautiful idea that gravity isn't some invisible force pulling us down. Nope. He said it's actually a curve in the very fabric of space-time. But, a beautiful idea is one thing. Proving it? That's a whole other ballgame. So how in the world did scientists manage to put the universe's most famous theory to the test?
Right, so that's the million-dollar question, isn't it? How do you even begin to test a theory that completely rewrites the rulebook for the universe? How can you possibly measure a curve in something you can't even see or touch? It was, without a doubt, one of the biggest challenges science had ever stared down.
Okay, so to tackle something this huge, scientists needed a game plan. They needed a totally fair, unbiased way to judge any theory of gravity. Think of it like a universal report card.
And that report card has a fancy name, the Parametrized Post-Newtonian Framework, or PPN for short. Now, I know that sounds super complicated, but the idea behind it is actually pretty simple. It takes all the crazy complex math and boils it down to just a few key numbers that we can go out and actually try to measure. And here's the really cool part, this simple, elegant rule at the heart of it all. For general relativity to be the correct description of our universe, two of those key numbers, called gamma and beta, have to equal exactly 1. Not kinda close to 1, exactly 1. If they came out as anything else, even by a little bit, the whole theory would be in serious jeopardy.
So let's crack open our first case file. Einstein made a jaw-dropping prediction. If mass really does curve space-time, then even something that has no mass, like a beam of light, should have to follow that curve. This means a massive object, like our sun, should literally bend the path of starlight that passes nearby.
And check this out. This is the first big test in action. Back in 1919, during a total solar eclipse, astronomers took pictures of the stars right next to the blacked-out sun. And what did they find? The stars' positions looked like they had shifted, just like you see on the right. Why? Because their light was bending as it grazed past the sun's massive gravity. It was the first, absolutely stunning piece of evidence that Einstein was onto something huge.
Of course, science never sleeps, right? Waiting around for solar eclipses isn't exactly efficient, and our own atmosphere can blur the view. So scientists leveled up and turned to these bad boys, radio telescopes. They can lock onto distant radio sources, like quasars, day or night, rain or shine, with incredible precision. This allows them to measure that light-bending effect way more accurately than ever before.
Now this is one of those moments in science that just gives you chills. Seriously, look how perfect this is. The little dots on the graph, that's the actual measured data of radio waves bending as they pass the sun. And that solid line, that's the exact path predicted by Einstein's equations. I mean, the data points fall right on the line. It's a perfect match. It's just, wow.
So what does this all mean for our rule of 1? Well, this experiment measures that first parameter, gamma, which basically tells us how much space gets curved by mass. General relativity predicts gamma has to be 1. And the result from the experiment? It came out to 1, with a tiny margin of error of just 2,000th. A spectacular, dead-on confirmation. All right, for case file number 2, we're going to dive into where Einstein's theory gets, well, even weirder. It doesn't just say gravity curves space, it also says gravity warps time. As in, time itself should literally tick by more slowly when you're in a stronger gravitational field.
I mean, how in the world do you even test that? Well, if it's 1976, you launch a crazy precise atomic clock on a rocket. Scientists sent one of these clocks 10,000 kilometers up into space where Earth's gravity is just a bit weaker. Then they compared its ticking rate to an identical clock on the ground. The result? The clock in space ticked just a little bit faster, exactly the amount Einstein's math said it would.
Then, scientists got even more clever. They used the Viking lander on Mars for a different kind of test. They'd send a radio signal from Earth to Mars and time how long it took for the echo to get back. But here's the trick. When Mars was on the far side of the sun from us, that signal had to travel deep down into the sun's massive gravity well and then climb back out again. And that journey took just a fraction of a second longer than it should have been, a delay caused by the sun literally stretching space-time.
The amazing thing is, both of these experiments, the clock on the rocket and the radio signals to Mars, are just different ways of measuring that exact same parameter, gamma. And they both gave the exact same result, gamma equals 1, with that same tiny uncertainty of just 2,000ths. It's an independent check with the same perfect outcome. You can see the evidence was really starting to pile up. Okay, on to our third and final case file. And for this one, we actually have to go back in time to a mystery that haunted astronomers for decades before Einstein even came on the scene. It's the very strange case of the planet Mercury.
See, according to Newton's laws of gravity, Mercury's orbit around the Sun, which is this kind of oval shape, should be fixed in space. It should trace the same path over and over. But it wasn't. Very, very slowly, the entire orbit itself was rotating. Now, astronomers were smart. They calculated the gravitational pull of all the other planets, but even after all that, there was still this tiny, nagging, unexplained wobble.
This is the number that broke Newtonian physics. A tiny little discrepancy of just 42.98 arcseconds per century. To put that in perspective, that's like the width of a human hair as seen from over 30 feet away. It's an incredibly small amount. But it was real, it was measured, and for over 50 years, nobody could figure out what was causing it.
So this test measures our second key number, beta. And beta is a little different. You can think of it as a measure of how nonlinear gravity is. In general relativity, the curve in spacetime, which is gravity, is itself a source of more gravity. It's like a feedback loop. And just like with gamma, for Einstein's theory to hold up, beta must also equal exactly 1.
And here's the punchline. When Einstein took his new equations and applied them to Mercury's orbit, what did he find? They predicted an extra little wobble of, you guessed it, 42.98 arcseconds per century, the exact, precise amount of the mystery wobble. He solved it perfectly. And when we measure the parameter beta from this, we get a value of 1, with an error of just 3 thousandths. Case closed.
So, after going through all the evidence, after opening all the case files, what's the final verdict on general relativity?
When you lay it all out like this, I mean, the evidence is just undeniable. Every single independent test, whether it was measuring how space curves with gamma or how gravity feeds on itself with beta, every test produced a result of exactly 1, right on the money. It's a perfect score.
And look, this isn't just some dusty old science experiment. This stuff is real, and it matters in our lives. The GPS in your phone has to constantly correct for these exact time warping effects of relativity, or it would be off by miles every single day. Confirming this theory is the bedrock for our understanding of black holes, for our ability to detect gravitational waves from colliding stars, and for building models of our entire expanding universe.
So for over a century, Einstein's theory has just crushed every single test we've thrown at it. It is without a doubt one of the most successful scientific theories of all time. But science never stops asking questions. The theory works perfectly here in the relatively calm neighborhood of our solar system. The next big question is, does it still hold up in the most extreme places in the cosmos, right on the terrifying edge of a black hole?